Hello, welcome to Fundamentals of Acoustics. Today is the start of the 10th week of this course, and over this week we will cover Fourier transform and fast Fourier transform for time series signals. So, what these techniques will help us do is convert data which is in time domain into frequency domain. So, last week we had seen that if there is a periodic function and the periodicity of that function is t seconds, then we can represent that time series signal in the frequency domain, and in the frequency domain we represent that in terms of two parameters. One is the amplitude of the signal corresponding to each frequency, and the second one is phase of the signal corresponding to each frequency. So, first what we will do is we will revisit those relations and see what they tell us as we change the time period of the signal. So, what we had said in the last week is that for Fourier series, if there is a signal which is periodic, then its periodicity can be it can be represented as a Fourier series such that f t equals a naught plus sum of a n cosine 2 pi n t over t plus b n sine 2 pi n t over t. So, that is n equals, so here n is equal to varies from 1 to infinity, and same thing here. Okay. Now, we realize that 1 over t equals f. So, another way of writing the same expression is a 0 plus summation of a n cosine 2 pi f n t plus p n sine 2 pi f n t, and n equals 1 to infinity, n equals 1 to infinity. And these coefficients we had defined them. So, what are these values? So, if we know f t, then a 0 equals 1 over t minus t over 2 to t over 2 f t dt. Okay. And a n, which are the coefficients associated with cosine terms, they are defined as 2 over t minus t over 2 to t over 2. So, I am integrating over these limits, and the integrand is f t cosine 2 pi f n t dt. Okay. And b n is 2 over t integrated over the limits minus t to t over 2 f t sine 2 pi f n t dt. So, these are the expressions for a naught, a n and b n, and these are constants which are there in the Fourier series. So, let us make some observations. Let us make some observations. These are important observations because they will be useful subsequently. So, the first observation is that suppose this ft does not change, but time period, its periodicity changes. If only periodicity is changing, then so the first thing is as t goes up, A0, AN, BN decrease, and if all things are same, then as time period doubles, A0, AN, BN they halve, and so on and so forth. So, this is one important relation, important trend we should understand. So, an equivalent statement would be as frequency. So, what is frequency? Frequency is 1 over t, right. So, as 1 over t decreases, so do A0, AN and BN. So, what is this frequency? This frequency is frequency of periodicity, okay, frequency of periodicity. So, what does that mean? That if the time period of a signal as it becomes larger and larger, these terms A0, AN, BN they become less and less. So, theoretically if time period is extremely large and if it is theoretically infinite, then these coefficients, if ft is not changing, they will approach 0. So, this is an important thing. The second thing to note is, so what is the second observation? So, let us look at ft, how I have expressed it. I have expressed it as A0 plus A1 cosine 2 pi ft plus A2 cosine 2 pi times 2 ft plus A3 cosine 2 pi times 3 ft and so on and so forth. Plus similarly we have a large number of terms in sines. So, the sine and cosine terms have frequencies of f, 2f, 3f and so on and so forth, where f equals 1 over t, right. So, the fundamental frequency will be f, which is 1 over t, then the next Fourier component will be 2f, third Fourier component will be 3f and so on and so forth. So, what does that mean? So, the separation of two adjacent frequencies is f, that is 1 over t. So, what does that mean? So, what graphically what that implies is that if I am doing the amplitude plot, if I am doing an amplitude plot for a function which is periodic in nature, then it will have, of course, it will have an A0 component which corresponds to 0 hertz, but then it will have its first frequency which will correspond to f, the second frequency will correspond to 2f, third frequency will correspond to 3f, and corresponding to each frequency there will be some amplitude, and so on and so forth, 4f, 5f, 6f. So, this is my f and this is the amplitude. So, it will be something like this, right, and the separation between these two frequencies, two adjacent frequencies. So, this is delta f is what, is equal to 2f minus f is equal to f is equal to 1 over t hertz. Now, think about it. So, this separation is 1 over t hertz. There are no frequency components between f and 2f. Okay. So, for a periodic function, so based on this we make an important observation. For a periodic function, of time period t, and we define f is equal to 1 over t, there are no frequency components between, let us say, nf and n minus 1 f. Okay. There are no frequency components. So, a periodic function may have infinite frequency components, but between two frequency components which are adjacent to each other, which are separated by f, there are no other intermediate frequency components. Fourth observation we make is, as time approaches infinity, what happens? This delta f approaches 0, right. As time approaches infinity, delta f approaches 0. So, what that means is that as time approaches infinity, this amplitude plot delta f. So, what is delta f? Delta f is this thing, 2f minus f is delta f, 3f minus f is delta f, right. So, it is f, and that equals 1 over t hertz. So, as time period is approaching infinity, 1 over t is approaching 0. So, what that means is that these points become extremely close, and when time period becomes infinite, then the separation between them is theoretically 0. So, what does that mean? That as time period approaches infinity, amplitude plot changes from a discrete plot. So, what is discrete plot? See, amplitude plot is right now, if time period is not infinity, then these points are separated by finite distance, right, and there are no intermediate points. But as t becomes infinite, then this amplitude plot changes from a discrete plot to a continuous plot. I mean, this is what continuous plot. So, this is an important thing to understand, right. So, if there is a signal which, so what does that mean? So, the last thing is, if there is a signal which repeats after infinite seconds, so what does that mean? T is equal to infinity, its amplitude and phase plots will be, then its amplitude and phase plots in frequency domain will be continuous curves. Okay. So, why are we discussing all this? So, till so far what we have done is that we have discussed that if I have a function which is periodic and its periodicity is t seconds, then I can represent it as a Fourier series. But consider a function which is not periodic, which does not repeat out itself, then I can say that this function is going to, in one set of words I say that this function is not periodic, or I can also equivalently say that this function is going to repeat itself after infinite seconds. So, what that means is that if I have a function which repeats itself after infinite seconds, then I will not get its transformation in a frequency domain as just dots, but it will be theoretically a continuous curve. So, the transformation of aperiodic signals. So, what is aperiodic signal? That is signal with t equals infinite is, so transformation of aperiodic signals in frequency domain is carried out by Fourier transform. Okay. So, what does a Fourier transform do? You have a signal which is not necessarily periodic, you use a Fourier transform and you can find out its frequency components, and at what frequencies you will find out these components. You will find these its components at all possible frequencies. So, you will find it at 0 hertz, 0.1 hertz, 0.001 hertz, 0.0001 hertz, and all possible frequency values you will find it will have some Fourier components. Okay. Why? Because of this understanding that as the time period is becoming very large, the frequency separation between 2 points is shrinking to 0. So, this Fourier transform helps us achieve this thing. So, this sets the background for more detailed discussion on Fourier transform, and that is something we will do tomorrow. So, till then please digest this basic understanding, what is it that we are trying to do, and then tomorrow onwards we will discuss Fourier transform in greater detail. So, till then have a great day and we will meet once again tomorrow. Thank you.